So let's take a look at some examples out of 8.5. So in this section, we'll be doing what is called partial fraction decomposition. We look at this problem as it is. If we let the denominator be u, then du would be 2x. And we don't have an x on top to go with the dx. We could get the 2, but we have problems if we're missing a variable. Also, since it's minus and not plus, this is not going to be arctangent. If it was u squared plus a squared, we have a formula for that, but not u squared minus a squared currently. So what we can do is we can recognize that this denominator factors. Let's come over and let's rewrite. Trying to freeze up on us. Let's rewrite 1 over x squared minus 81 as two separate fractions. Now, how do we do that? If it was a product on bottom, we could write it as a product, but we don't really have a product rule for integration. So how can we write it as one thing plus or minus another? Notice that denominator is factors. And if you took Math 112, one thing we discussed is that if we have a product on bottom, we can separate this as something over one factor plus something over the other factor. And our goal is going to be to find out what values go on top such that when we add these fractions together, it gives us what we started with. Now, fractions have to be proper fractions in this case, meaning that the degree on top has to be smaller than the degree on bottom. So if this is x to the first, we can't have any x's on top. We can only have constants. Same thing here. If this is x to the first, we can't have any x's on top. So we're going to ask ourselves, what numbers do we need to put on there so that when these are added together, we get 1 over x minus 9, x plus 9, or 1 over x squared minus 81. So to find these values, remember what we do is we're going to put these back together momentarily using our common denominator. So the first fraction already has an x minus 9 on bottom, so we have to pick up an x plus 9, and if we pick up 1 on bottom, we have to pick up 1 on top. The second fraction started out with an x plus 9 on bottom. If we pick up an x minus 9, we have to also pick 1 up on top. Now, this fraction and that one are the same, this one and that one. And since we have the same denominators, we can keep our denominators and add our numerators. So a times x plus 9 plus b times x minus 9. That's equal to what we started with, 1 over x minus 9 times x plus 9. So what we've accomplished is we've gotten a relationship between this numerator and a and b. If we have a fraction equal to a fraction and the denominators match, then the numerator also. So 1 has to be a times x plus 9 plus b times x minus 9. Now for ones like this, where we have unique denominators and none of them are repeated, then there's a special way that we can solve for a and b. And that's by picking specific values of x. For example, if we let x be negative 9, notice what's going to happen. If we put a negative 9 in here, we get 0. If we put negative 9 in here, we get negative 18. So that 0 makes that term go away. So we get 1 equals negative 18b. And to get b, we divide both sides by negative 18. So b is negative 1 over 18. Now, let's pick another number for x that would make that term go away instead. So if we pick x equals 9, if we go in this equation and put in the same equation and put a 9 in for x, we would have a times 9 plus 9 b times 9 minus 9, so that cancels. So 1 equals 18a, or a equals 1 over 18. So those are the values that we need for a and b, so that those two fractions combine to make what we started with. So that means that our integral we can rewrite as 1 over 18, all of that over 8 minus 9, plus negative 1 over 18, all of that over x plus 9. And of course, we wouldn't leave it as an improper fraction like this, but the reason I did that is we can pull the 1 over 18 out front, and we can say that times the integral of dx over x minus 9, and then we can pull the other 1 over 18 out front and say that's times the integral of dx over x plus 9. So we just pulled our constant out front. Now both of these integrate into natural log. If the denominator is u, the derivative of the bottom is just 1 dx. So that's du. If that's u, that's the derivative of u. The du over u integrates into natural log absolute value of u. Natural log absolute value of u plus c. And I would be fine with you leaving it like that. The answer that they show, we could factor a 1 over 18 out, and that gives us this. And one of our properties of logarithms say if we have a log minus a log, then we can combine that into a single logarithm where the positive log, that factor goes on top, the negative one, that factor goes on bottom. So we've combined those into a single logarithm. So we were able to integrate that. The biggest thing here is remembering how do we do partial fractions. Okay, so let's take a look at this one. Notice to begin with that the degree on top is bigger than the degree on bottom. That means this is an improper fraction. So if we're dealing with improper fractions, we have to divide this out and change it to a proper fraction before we do anything else. So unfortunately, synthetic division would be probably worse on this one than regular division, because we don't have a binomial with x to the first power on bottom. We have a quadratic. So we have 2x cubed minus 4x squared minus 95x plus 27, and we're going to divide that by x squared minus 2x minus 48. So remember how this works. We take this leading term divided by that leading term. So 2x cubed divided by x squared makes 2x. Once we get that, we take that 2x times everything out front. So 2x times x squared, 2x times minus 2x, 2x times minus 48, and then we subtract. We take the top one minus the bottom one. The top minus the bottom. Minus a negative makes that a plus, so that's 0. The top minus the bottom. So again, that's a plus, so that gives us 1x, bring down the 27. Once we get to the point where this degree is smaller than that degree, we can't divide anymore. We can't take 1x and divide it by x squared, because that's going to leave us a fraction. So we take our quotient is 2x, and then we add our remainder over the divisor. So this expression is equivalent to what we started with there. Our quotient plus the remainder over the divisor. So as we did on the last one, we're going to break this apart. If we just picked the denominator to be u, the top is not going to be du. And it would be messy to try to make that happen. So what we can do is we can factor the denominator into x minus 8, x plus 6, and then we can find out how can we rewrite this fraction into two separate fractions. How can we take x plus 27 over x minus 8, x plus 6, and rewrite that as something over x minus 8 and something over x plus 6. So we're gonna, since now that we know what the form of our fractions is going to be like, we reassemble these so we can relate this to this numerator. So our common denominator, x minus 8, x plus 6. So if we pick up an x plus 6 here, we pick one up on top. We start out with an x plus 6 on bottom. To get this denominator, we need to pick up an x minus 8, so we do that on top and bottom. So both fractions have x minus 8, x plus 6 on bottom. So to put them together, we take the first numerator plus the second numerator. So that should equal what we started with. And since those denominators match, the numerators also have to match. Otherwise, they wouldn't be equal. So that tells us x plus 27 and a times x plus 6 plus b times x minus 8, those have to be equal to each other. So, different ways to do it, but if this factor only occurs once and this one once in this equation, then we can just pick specific values of x so that we can find a and b. Or if we had 3 terms so that we could get a, b, and c. So if we replace x with negative 6, we're going to get 21 equals a times 0 plus b times negative 6 minus 8, negative 14. So negative 14b equals 21, or if we divide, then b is negative 3/2. 7 goes into that, 7 goes into that. All right, if we let x equal 8, 8 plus 27 is 35. 8 plus 6 is 14, so 14a. 8 minus 8 is 0, so that term is 0. So divide both sides by 14. So a is 5/2. 7 goes into 35, 7 goes into 14. So we have 5/2 here and negative 3/2 here. So that means we can rewrite our integral as 2x plus 5/2 over x minus 8 minus 3/2 over x plus 6 times dx. Make sure I copied that right. Yeah. So we decompose this fraction into two separate fractions. So now we just try to integrate. And then we're going to pull the 5/2 out and integrate dx over x minus 8. Pull the 3/2 out, integrate dx over x plus 6. So for the first one, we're going to do power over that power. For this one, if this is u, this is the derivative of that, So that's natural log absolute value of u. Same thing for the next one. If that's u, that's du, so that's natural log absolute value of x plus 6 plus c. Those 2's would cancel, so we'd be left with x squared plus this minus that. No real advantage to combining those, so we can leave it just like it is. So both of these examples dealt with partial fractions where our denominators had binomials as factors, and each factor only occurred once, and they were linear. In the next example we're going to look at the case, well, what if we have a factor on bottom that's quadratic? How do we simplify that? So let's write this. Notice this denominator does not factor anymore. This is prime, so we are going to have an x on bottom, and we are going to have an x squared plus 1 on bottom. Now, after we do this example, we'll look at what happens if one of these entire factors is squared or cubed. But in this case, as in the cases before, each factor occurred once. We have this factor once and that factor once. Okay, so we're going to list those denominators. Since this is x to the first, we can only have a constant on top. But since this is x squared, we can have an x to the first on top. So we could have a certain amount of x's, and we could also have a constant. So let's say that again. For this to be a proper fraction, if this is x to the second, we can have some x to the first, and we can have some constants. So we're going to have to find out what does a, b, and c have to be so that when we combine those gives us this. Now the next step is going to look just like what we did on the other ones. We're going to combine these so that we can get a relationship. That's going to be our common denominator. So if we pick up an x squared plus 1 on bottom, we do that on top. For the next fraction, we need to pick up an x so that we have that denominator. So if we pick up an x, we have to pick one up on top. So now our denominators are both x times x squared plus 1. So we're going to take the first fraction, or the first numerator, plus the second numerator over the common denominator, and that's got to be equal to x plus 1 over x times x squared plus 1. So since the denominators match, then that means the numerators have to match. Now this one is going to be a little bit less straightforward than the other two. On the other two, we simply picked a value for x, and when we plugged that number in, we were able to find one letter, and then we plugged the other one in to find the other letter. This time we have 3 different letters, and it's not going to be quite as easy as just plugging in a value for x. So what we're going to do in this case is let's go ahead and get rid of our parentheses. If we distribute, we have ax squared plus a plus bx squared plus cx. If we group like terms together, those are both x squareds, so to see how many x squareds we have, we add their coefficients. We only have one x term, and then we have only one letter that's by itself. So we have x squareds, we have x's, and we have a constant. So for these two sides to be equal, the coefficient here has to match the coefficient of x squared on the other side. The coefficient of x here has to match the coefficient of x here. And the constant here has to match the constant here. In order for these to be equal, we have to have the same amount of x squareds, the same amount of x's, and the same amount of a's. So on the right side, we have a plus b. That's how many x squareds we have. On the other side, we have no x squareds. So we need our coefficient of x squared to be 0 so that they match. On this side, the coefficient of x. On the other side, the coefficient of x is 1. And on this side, our constant is a. On the other side, our constant is 1. So notice those have a and c by themselves. The only unknown we don't currently know is b. But if we substitute in, a is 1. So a over 1 equals 0. Subtract 1 from both sides, and now we know b. So if we put that back in, then we have 1x, 1 over x, negative 1x plus 1 over x squared plus 1. So that's how that separates. Plus negative 1x plus 1 over x squared plus 1. We want to integrate that and evaluate it from 1. Okay, so we look at integrating this. The first term just integrates into natural log absolute value of x. Then for the next one, question is, how are we going to do that? If we let the bottom be u, then du would be 2x dx. Well, the thing that gives us a problem here is that we have two separate terms. If we just had an x here, we could put a 2 with it and then a 2 out front. Or if we just had a 1 here, we would actually use an entire different formula. So let's separate this. Let's call this minus the integral of x over x squared plus 1. Notice I just pulled that minus 1 out front. Plus, and we've got to have a dx, plus the integral of 1 over x squared plus 1 dx. So minus 1x over that plus 1 over that. Got two different integrals going on here. For this one, if we let u be x squared plus 1, du is going to be 2x dx. So if we pick up a 2 here and divide by 2 out front, then we're going to have minus 1/2, and that's going to be du over u. So natural log absolute value of u. What about this one? If that's u, du is 2x. We don't have any x's up top. But notice what this is. This is u squared plus a squared, where u is x, du is 1, dx, a is 1. And you may recall that the integral of du over u squared plus a squared, that's arctangent. That's going to integrate into arctangent u over a. I think it has a 1 over a out front also. But since our a is 1, so we are going to integrate into arctangent u over a, which is 1. And we're going to evaluate this from 1 to 3. So we're going to put 3 minus 1/2 natural log of 3 squared, 9 plus 1, so 10, plus arctan of 3. And then we're going to plug in a 1. We're going to do natural log of 1 minus 1/2 natural log of 1 squared, so 1 plus 1, plus arctan of 1. And we're going to put that in our calculator and get a decimal. So out front we have natural log of 3 minus half of natural log 10 plus, let's see, we want to be in gradient mode, plus arctan of 3. So that's the first parenthesis, and then we're going to subtract natural log of 1, which is 0, minus 1/2, so negative 0.5, times natural log of 2, plus arctan of 1. Close that parenthesis, and we get about 0.758. So again, the biggest thing here, well, several big things, is first of all, how do we break that apart? Something over x, something over x squared plus 1. Once we decompose that, then we have to recognize how we're going to integrate that. Two terms on top, put each term over the denominator. And then when we do that, then it goes back to what is going to be the formula we use to integrate that. If this degree is 1 smaller than that, then try letting this be u and see if we can make du. If this degree is not exactly 1 less than that, here we're going to try u squared plus a squared, and that's what it ended up being. Real quickly, let's make a comment. What if we have an x over x plus 2 squared as our factors? Well, we're going to end up with an x on bottom, x plus 2 on bottom. Since that's x to the first, we can only have a constant on top, but we could also have an x plus 2 squared. So if we have this factor repeated, we're going to have different fractions where we have this starting at the first power and going up to that power. So if this was a 3, we would have x plus 2 to the first, x plus 2 to the second, and an x plus 2 to the third. Our numerator is going to be 1 degree less than the base factor. Even though when this is squared, that would become quadratic. Since our base factor is x to the first, then that's only going to be a constant. We're not going to have one this messy, but if we had, let's say, an x squared and then an x squared plus 3, let's actually make this here and a squared there. So we have this factor repeated 3 times, so we could have an x squared, and an x cubed on bottom. That base factor is linear, so we would only have constants on top there. This factor is repeated twice, so we have an x squared plus 3 to the first, and then we would have it to the second. Since this factor is quadratic, we could have x to the first and a constant, an x to the first and a constant. Now, we're not going to have one that has that many fractions, but just to illustrate what you do when you have a repeated factor.